Hello guys, welcome to my channel again. In today's session, we are going to see Obermarck's algorithm. In distributed system, we can find out the deadlock by using three types of mechanisms. First one is centralized, then is decentralized, and the next one is hierarchical algorithm. In centralized algorithm, we have already discussed about Ho Ramamurthy phase 2 algorithm. Now, let us see one algorithm which is having decentralized approach. This is also known as path pushing algorithm. The name of this algorithm is Obermarck's algorithm. This technique is used in the distributed system to handle deadlock detection. So deadlock recovery is not there in this mechanism or in this algorithm. In distributed system, detecting deadlock is challenging because no single node has a global view of the entire system. We know that distributed system is itself distributed among different nodes. So multiple nodes are there, multiple sites are there which are geographically separated, and every site is having n number of processes and n number of resources. So all this thing is distributed, right? And these processes and resources are interacting with each other. Now, if this is the situation, then we definitely can say one statement that all these nodes are geographically separated. So every node will be having its own information, but it is very difficult to maintain the global view of the entire system on every node. So with the help of Obermarck's path pushing algorithm, we address this problem. We achieve this thing by propagating information about transaction dependencies, we call it as path, across the distributed system to detect the cycles or deadlock. Obermarck algorithm works in 8 stages. So let us start from step number 1. First of all, it is mandatory to understand the distributed system setup. A distributed system consists of multiple nodes. So these nodes might be geographically distributed. So I have shown 4 nodes over here. Suppose node 1 contains 5 processes and 10 resources. Node 2 contains 10 processes and 5 resources. Node 3 contains 13 processes and 20 resources, and node 4 contains 1 process and 10 resources. And likewise, as this is a distributed environment, any process which is getting executed on any node may require the resource which might be there on any other node in the distributed environment. Transactions may span multiple nodes, and dependencies can form between transactions across the nodes. Each node has information about its own state. So based on that state, every node can create its own local wait for graph. But initially there might not be a single node which might be maintaining the global state of the entire distributed system. That is the challenge that we need to resolve with the help of Obermarck algorithm. So first step tells that every individual node will maintain the information about its local state in terms of wait for graph, because that node is aware with the dependencies between the processes and the resources which are there on it. Let's go to the step 2. Path is a sequence of transactions where each transaction is waiting for the next one in the sequence. For example, we have transaction T1. Transaction T1 is waiting for transaction T2. Transaction T2 is waiting for transaction T3, and likewise. So suppose if I draw a small diagram, this is node number 1. Node number 1 contains 3 transactions, transaction T1, T2 and T3. So T1 is waiting for T2 transaction and T2 transaction is waiting for T3 transaction. There is a dependency between these transactions. We have seen this similar type of dependency when we studied wait for graph or when we studied resource allocation graph. Now if these transactions are dependent on each other, we can represent it with the help of the path, that is T1 is dependent on T2, T2 is dependent on T3. But now in this case we have considered the transactions on only one node, but sometimes there might be different nodes and the transactions of one node may depend on the transaction of the other node in the distributed environment. In short, we can say that the transaction which is there on node 1 may depend on the transaction which is there on node 2. So all this type of dependency of the transaction is represented with the help of the paths. So in step number 3, every node examines its local WFG and identifies all paths starting from its local transactions. For example, suppose node A has a local path in which transaction T1 depends on T2 and T2 depends on T3. Now, this is what node 1, this is node 2, this is node 3. Now, when a transaction involves transaction on another node, for example, T1 and T2 transaction are getting executed on node 1, but T3 transaction is getting executed on node 3. T1 transaction is dependent on T2 transaction, where both T1 and T2 transactions are residing on node number 1, but T3 transaction resides on node 2. So in that case, we can say that when a path involves transaction on another node, here in this case T3 is a transaction which is getting executed on another node, the node pushes the path to the relevant node. So here it means T1 T2 path will be formulated at node 1, but this path is pushed to node 2. So for example, if T3 is located at node number B, consider this is node number B, node A sends the path T1, T2, T3 to node B. So this path T1 dependent on T2, dependent on T3 is pushed from node 1 to node 2 or node A to node B. This process is known as path pushing, and it enables the nodes to exchange the information about the dependencies. When a node receives a path, now in this case node B has received the path, it checks if the last transaction in the path is waiting for any local transactions. So it means that if node B receives the path T1 dependent on T2 dependent on T3 and T3 is waiting for T4, so there might be two cases. Either T4 might be a local transaction to node B, or T4 might be a transaction which might be getting executed on node 3. Now if T4 transaction is getting executed on node 3, then again node B has to push the path, that is T1 dependent on T2, dependent on T3, dependent on T4 to node 3. So in this way the path pushing will take place across the distributed environment, but the condition is that the last transaction in the path should wait for any other transaction which might be getting executed on another node. In this case T3 was dependent on T4 and T4 was getting executed on node 3. So in short we can say that if the extended path involves another node, the process repeats and the path is pushed further to the next node. So now let's see step number 6, that is detect cycles. Now consider one scenario. This is what node number 1 and this is what node number 2. Node number 1 contains T1 and T2 transactions. Node number 2 contains T3 transactions. So T1 dependent on T2 and T2 is dependent on T3. If T2 is dependent on T3, then this path is pushed by node number 1 to node number 2. So node number 2 will receive the path T1 is dependent on T2, T2 is dependent on T3. But now the important point here is T3 transaction again depends on T1 for its execution. So what is happening here, the complete cycle is getting formed. So if there is a cycle, then eventually the complete path will loop back to the transaction which has initiated this path. So in this case node 1 has initiated the path, and then after following the dependency the path is coming back to node 1 itself. If this type of thing happened, then we can say that there is a cycle in the distributed environment, or there is a deadlock in the distributed environment. So what is the solution for that? So solution is, so when the cycle is detected, we need to terminate one of the process from that particular cycle. After detecting the cycle and after terminating one of the process, so we can come out of the deadlock. So once the deadlock is detected, system resolves it by selecting a victim transaction, and system aborts that transaction and it allows other transactions to proceed. So this is what the end of the Obermarck algorithm. So that's it from this session. I hope that you might have liked this session. Kindly like the video and subscribe to my channel. Thank you.